So what I was getting into is that most of this today is like review stuff. So it's up to you guys if you guys want me to go like deeper into it or like repeat some of the same stuff. I can if you guys want. But for the most part, I believe this is the same, almost all the same material from section 8. And this is of course section 8 of version 1, which is like always confusing. But basically, I think if you guys have gone through it, and just give me a thumbs up if you guys have gone through at least part of this section 17, at least maybe looked at it. Okay, cool. All right, so see Andrew goes down. That's okay. As Ali and Thomas, you guys probably saw most of it, if not all of it, like not all of it, but like most of it, except for the last few sections in particular, are things you guys already seen. So it's not something, I would say like I would approach this as a, how do I call this? As a chance to kind of review parts of probability. And the reason why is because the next few sections coming up, when we're going to talk about other parts, the statistics and the probability and the mathematics are really important to kind of get an idea of. It'll help you understand, especially I think, I'm trying to remember what's, it's all mixed up in my head right now because we're on version 2, section 17. So like the few sections coming up, which I believe are section 19 and 20, for this would be like next week, we're going to be dropping into like MLE and stuff, and understanding combinations and probability in general will help you get a better grasp of these more, in my opinion, sometimes to be a little convoluted like mathematics, especially MLE. I think most people kind of have a little, what's it called? Like uneasiness with MLE just because it's a little confusing at first, but it's all based around probability. So yeah, so okay, so we'll get into it. So I guess I'm trying to grab at my notes real quick. This one was an interesting one to kind of go into. So I'm going to give like a little bit of primer going into this. Primer? No, primer. Okay. Let me just actually pull up the lesson because, as you guys probably noticed, it's confusing in my head too, going from version 2. The good news is that after section 18, all of it will be new for you guys. There won't be any worries. Section 18, which is next after this one, will be some review, statistical distributions, but there'll also be a lot of new parts of statistical distributions. So you'll see that in there too. Okay, so let me go ahead. I'm just gonna share my screen so you guys can, let's see here, share and share. Okay, and of course Zoom puts my windows over in random spots because why not? All right, so this is just, I'm just kind of showing you guys the lesson, so kind of going through. So this is section 17, like I said, combinatorics. I don't even know what the ending is there. I'm gonna say top combinatorics and probability. I don't know if it says on here, maybe. Oh, this is probably it right here. Yeah, that's probably what that phrase is. This is cut off for me. But combinatorics and probability, basically everything from here down to about, I'm gonna say up to combinations at least is section 8. I believe conditional probability is new for you guys. I could be wrong, but I definitely know law of total probability and simulations with conditional is a newer section for you guys. These would be ones that you had not seen at least. You might be familiar with it or find it relatively easy because you understand this stuff, but these are different from section 8. Probably conditional probability too. So I'm going to quickly just go through a few things like with sets, just kind of remind you about the notation. We'll talk about the introduction to probability, which again, we've already seen, so I'm not going to spend much time on it. And then permutations, factorials. We've seen this before, which I know everyone just loves factorials and permutations, combinations. I know that's one that's kind of hard to wrap your mind around, but mostly it's just ordering of things. I think as you see more problems, you get used to it. So this is actually a great place, even if you've done the lab before, it might be kind of a good thing to kind of like try to do it again and see if you can kind of reproduce it, especially if you're finding the time. So that's kind of a good thing to do. And then we'll talk about conditional probability, and we'll probably touch a little bit on law of total probability. All right, sound good? Cool. All right, so let me go ahead and pull up some notation on stats and stuff like this. So this is, and then this should be familiar to you guys. For you guys have already seen this. But basically just some notation. So we have, like, for example, our sets of space, our event spaces, our sample spaces. These are kind of terminology you should know. If you think of a space, or like sometimes we'll call it like a set, is basically just a group of things. And in mathematics, when we say like set theory, when you hear that, just know that basically means like it's a group of things without having to like use the word count, essentially. So you'll hear like mathematicians saying it like in the baby form and being like, a set could be like 3 different sheep, you know? A set could be like all the apples in the world. A set could be all the possible things that you could ever think of could be the set of things. Basically, it's a way to describe this part. So a set of event spaces, or probability space, we call it, is basically all the things that could possibly happen in the situation. So for example, the set of all coin flips, you can think of it as heads, tails, and then there's maybe like a third one you might want to count, which is like landing on its side or something, like, you know, perfectly on its side, which is really, really unlikely, but could possibly happen. Fun little story. I actually had a coin drop once. It was exactly to be a coin, so a little wider, but it hit the ground, spun around, and perfectly stopped on its side. So it does happen. I've seen it happen. Unfortunately, no one else was around me to see this happen at the same time, so they had to believe me that I was not like messing around. This is back like in middle school. Like, this is how long ago like it was. I've never had it happen again, but it is technically possible. So again, those would be the event spaces. So no matter how unlikely it is part of that space. You can also have parts of your space of multiple events. So for example, it's like all the space of all 2 coin flips. Like, what are the possibilities of those 2 coin flips? Well, it could be heads, heads, it could be heads, tails, it could be tails, then heads, and it could be tails, tails. And then you could maybe throw in sideways, but we'll just use those basic ones. And so again, event spaces, I think they're relatively easy to understand. We usually represent it with a capital letter. Like for example, you see A and B are really common in probability. This capital P right here, usually this is representing like a measure, saying like, you know, what's the probability of this? So we talk about measuring with probability. You'll sometimes see, for example, if you're familiar with the mathematics, you'll see like these kind of like, not italics, I don't know, like kind of stylized Z's and R's and N's. These are represented also as sets. They're specific kind of sets. Capital Z with this kind of like stylized signature, those are the integers. So all the positive numbers, all the negative numbers in 0. R right here is the real number. So basically every single number that isn't imaginary hasn't basically the square root of I. So those are like fractions, decimals, pi, those are all real numbers. And then I didn't have one here, but basically there's also the natural numbers, which is a similar kind of stylized thing, but an N, which depending who you talk to, natural numbers includes 0 to basically all positive integers. So like 1, 2, 3, 4, 5, all the way to infinity. Some people include 0, some people don't include 0. I've had people argue that it shouldn't be included, but either way, just know it doesn't really matter if you can include 0 or not, you just write it differently. So that's kind of like what those like letters represent. And you can see here, this E, for example, is event spaces, okay? This one right here, again, hopefully this review, let me know if I'm going too slow, like if you guys are like, this is like too basic, we already learned this. But this symbol right here, I actually don't know what it's called outside of like math essentially, but usually it's represented with a 0 or like a circle with a slash through it, which is not 0. This is represented as the empty set or the null set. Basically, it's the set with nothing in it. So you can say like, what is the set of nothing? That's the empty set or the null set. Okay, so that's what this is represented by. So this is kind of giving you some mathematical like background to make sure you understand how to read papers or read something else someone's writing about. Okay, this right here, this is basically the intersection. So this right here is basically saying A intersect B or A and B, so A and D. You can kind of translate it that. Basically, it's where these 2 sets intersect, where they have common ground. Kind of the opposite of that is our union, which is nice to remember. It just looks like a U. So union could also be like or, so like A or B. So basically, and also know when we say or in probability in computer science, we don't mean the exclusive or. So usually I say like you can have a salad or fries. What I really mean is you can have salad or you can only have fries. You can't have both of them. In computer science, we say or means both. So if you were to say to a computer scientist, can I have salad or would you like salad or fries? They said, yes, I'd like to have both. That's perfectly valid. That's kind of what I mean by or here, but that's what that union represents. And so in probability, we can basically say is that there's a few things we can go around this. Usually we'll see like in set theory and like probability theory is that we'll usually draw out spaces. And again, this is probably stuff you've seen before, but like this is like the set of A and this is like the set of B. And so for example, A and B or A intersect B would just be this part right here, basically that the sets that would cross over. This is like this sample that would be crossed over, represented by this. We also could have A or B, which could basically includes all of A and all of B. Okay, so this is not a big deal. There's some overlap, right? So by definition is that the probability of A union B is always like smaller or equal to the probability of A plus the probability of B. Hopefully that makes sense, because basically it's that this whole thing is like, if I did A and B all together, there's a little bit of overlap, so I'm discounting that. If they were completely separate, or we call disjoint, okay, if this was A and this is B, it would be perfectly just the probability of A and the probability of B. All right. So hopefully that doesn't seem too obvious. Like I like to say, like probability sounds really simple. Mostly it's just basically knowing how to count in general. That's essentially what we're doing in probability. It's just that we start generalizing, and that's when it starts getting a little more complicated. Okay, so any questions so far? I'm pretty good so far, looking good. Okay, cool. Yeah, and some basics about probability, again, things you already know. Usually represent the probability of being equal to 1. So the probability of the whole event space is equal to 1. So basically, if I had like all different like events happening, like you can have, oh, is my internet going all right? Okay, I might disconnect for a second, but I'll be back in a second. Okay, is that good? All right, cool. Sorry, my computer, I have 2 different Wi-Fi signals, and for some reason my second Wi-Fi signal doesn't like it. So I saw my thing come up. I'm like, okay. All right. So anyway, I lost my train of thought for a second, but I think the law of total probability basically is that if you have your whole event space, if you have all events A, B, and C, coin flipping heads, tails, sideways, if you have all that probability will always equal to 1. Okay, you can't have more than 1. You can have less than 1. In that sense, being like, oh, only A and B are considered, and maybe like a small sliver of probability is to event C. But the point is that we have it all to 1. Okay. All right. And then a quick notation on here. This is kind of, if you've never seen like a lot of math, this is kind of can be a little intimidating. But basically, just know that this is representing a whole set, another like event space in this case. And basically, you'll see this curly brace right here, okay, around here, and basically it's saying X. I'll read this out and then I'll kind of walk it through. So it's X such that X is inside of the set of integers, and X is less than or equal to 0, but greater than or equal to 0, but less than or equal to 20. Okay. So what this is basically saying is like, all right, this E, this event space, is going to include all X's, and X is an integer, but X has to be greater than 0, but less than 20. So, or less than or equal to, right? So basically this would include 0, 1, 2, 3, 4, all the way through 20. Okay, so this is kind of like this bar straight up usually means such that, or given that, kind of thing. And we'll see this a lot in probability, but this is also comes from set theory. Similar right here, you can see the event spaces right here. It's basically X such that X is in R, or is in the set of all real numbers, such that X is greater than or equal to 6. Okay, so basically say, oh, X is a real number and X has to be greater than or equal to 6. So that'd be 6, 6.1, 6.2, 7, 8, infinity. Well, I don't know if we can say infinity, but like, like as large as we want in those little smaller and smaller increments. Okay, so that's kind of like this notation. Any questions so far? And this should be kind of a review. Cool. Okay, and then I just wanted to show this, the law of relative frequency. We basically say is that we define probability. Probability is a weird thing when you think about it. Probability is that we're saying that there is an actual thing. So for example, if I say, what's the probability of flipping a heads or tails? You would say 50%, right? 50-50, right? How do you know it's 50-50? Well, we repeat it all the time, but basically it comes down to the fact that we say, well, if we keep flipping a tail over, or sorry, flipping a coin, and it will land either the heads on or tails. And if we keep doing that over and over and over again, we find out that we would expect, I should say, is that we would get about 50% as we flip coins more and more. So if I flip one time, right, it's only be heads, right? But maybe it'll be tails. If I flip it 10 times, we might get 5 heads and 5 tails, but we'll more likely get something like, oh, we might get a 6 and a 4, or a 4 and a 6, or a 3 and a 7. Or if we're really lucky, we get all 10 heads, right? That's totally possible. The point is, though, if we increase the size larger and larger, if we flip the coin 100 times, 1,000 times, 1,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times, all of these things basically will go into approaching the true probability. And this is what this is representing here, is that basically if we have this as our sample and we do n times over and over and over and over again, basically we would approach the actual probability of the, like, I like to imagine it like the truth of the universe. And that's essentially what the probability kind of says. Like, we don't really know what probability, like essentially, I don't know, I'm not going to go into full philosophy thing, but anyway, just know that the probability is kind of like the truth of like whatever this system is. We can figure this out by doing this system. And that's what the law of relative frequency is. Any questions or any comments? Cool, sound good? Yeah, all right, awesome. So that's probability, going through that. Event spaces, we talked about this. Permutations, combinations, usually, you know, I take a little bit more to go through this, but we've seen it before. My suggestion is just kind of walk through it a little more. I think this is literally the same like lesson I showed you guys from before, like back in section 8. But just basically know is that we have permutations, okay, and combinations. Permutation basically means that order matters. So if I say like use the letters A, B, and C to make a 3-letter word, which a 3-letter word could just be any letters, doesn't have to be an English word. So ABC would be a word, CAB would be a word, CBA would be a word. Those would be a permutation of some sort. If I said something like, hey, you need to make a word of A, B, and C, and D, but only use 2 letters, that would still be a combination, or sorry, a permutation. Okay, it's just that we're restricting how much. And this basically comes from this basically, I think we talked about this in the problem before, and how to code this. That's permutations. Permutations tend to be a little easier than combinations to deal with. Combinations are basically when order doesn't matter, okay? Is that basically we might have something where we have to consider, will C be, let's say, picking 3 letters of like 4 letters total. So we have A, B, C, D, right? A, B, C, D, yeah. And we pick 3 of those. A, B, C, and C, A, B would be considered the same thing. That's when we have to consider a combination. And you can see here very closely, it's basically, we call this like n choose k, right? But basically it's the permutations divided by another factor, which makes sense, hopefully, is that if order doesn't matter, you just have less possibilities, right? It doesn't matter if you go read it backwards or forward or mix them up, okay? So that's permutations and combinations. I'm not gonna go into full detail unless you guys would like me to. Any questions, comments? No, thumbs up right now, thumbs down for understanding. Sorry, I was on this understanding. Okay, cool. Hopefully this is feeling all review.